Okay. Um, we in our last class we tried to talk about the gradient boost algorithm, and just a recap of the things we said is that how this algorithm works is that when you give it your data set, for example, let's say we want to use say your feature is age, your feature is say age, and then your target is say salary. For example, salary is your target, for example. So say your target is salary. So let's say we just get our data, say age 20, 30, 40, and 50. And here we get salary like say 30,000, 50,000, 60,000, and then we say 45,000, for example. Assuming this is our data. And so we said, once this data gets to the first model, the basic model, model one, you are going to get pret one. And it's just going to be a summary, it's going to be an average of all of these. So this will be 330 plus 50, that's 80 plus 60, that is 140 plus 45, 185 divided by 1, 2, 3, 4. Madam Pair, what is the answer? 185 divided by 4. Mm. Mm. That should give us 71.5. So let's just say 71 for the sake of ease. So we're going to have 71, 71, 71, 71. And so we're going to calculate the first residual one. So our residual one is going to be, 300 this 71,000. So that's 30 minus 71 is going to be what? 41 minus 41 minus 21 minus 11 and minus 45 minus 71. What's 45 minus 71? 40 minus 70, 35, 34 minus 34. Oh, is that correct? Wait, 70, 40, 30, right? Minus 5, 25 plus 1, 20, 26 minus 26. So this is going to be our residual one. And so now we are going to now give this data and this one to model 2. And what model 2 will do is that model 2 will now form a decision tree. And on that decision tree, maybe let's say um, age greater than age greater than age less than 30. Here we are going to have minus 41 here as a prediction for 20. And then this way we are going to have three values, minus 21, minus 11, and minus 26, right? For this, and this, because they are not less than 30, right? And so this is already becomes a pure node, and then this one now can be further broken down, right? Into when you have another feature before you can now do another split here again. So now, according to our, so once it does this, then our prediction becomes this. So we're gonna get prediction spread 2, because this is spread 1. So we are going to have spread 2. And we're going to have here minus 41. Maybe this one is minus 21, minus 11, minus 26. And then we're going to have final prediction. Final prediction is spread 1 plus learning rate multiplied by what? Spread 2. That's what we know. Spread 2. And so if we do that, if we take a learning rate of 0.1, if you take 0.1 multiplied by 41, what is that going to give you, Madam Pearl? It's like saying 41 divided by 10, that should be 4.1, right? This one will give you negative 2.1, 2.1, negative 1.1, negative 2.6, right? Is this going to be the final rate? No, this is not final rate, sorry. And then you add that to spread 1. Sorry, I'm not crazy. I have to delete all of this. What was I calculating here? So our final prediction, we did all of this in our class. It's going to be prediction 1 plus learning rate. If our learning rate is 0.1, our learning rate is 0.1 multiplied by spread 2, this will be this plus this. So when you add this, and this, it should give you 71 minus 4.1. That should give you something like 670 minus 4 gives you 66 plus 1, 67. So it's going to be 66.9. This one is going to be 71 minus 2.1 should give you 68.9. And then this minus 11 should give you, minus 1.1 should give you 69. 70, is this 69.9 or 70.9? 69.9. 69.9, that's correct. We're going to give you 69.9, and then this one down here is going to give you what?
68.4.
Okay. I'm going to 68.4. Okay. So this is going to be our final prediction for model 2 based on the data. So this is what we talked about in our last class. So, and we said, this is what the gradient descent does. This is what it does. Perfect. Perfectly fine. This is what it does. Right. Now, we agree this. Now, the XGBoost system is built up from the gradient descent. So XGBoost stands for extra gradient descent. That's why XGBoost, extra gradient descent. XG, then boost, stands for extra gradient descent, and then boost. So it uses the same thing. And we said the advantage that comes with this one is that it takes care of overfitting by pruning. Overfitting by pruning, we said this in our last class. And then we also said that it does multitasking. So therefore, making the training and the performance of your algo to be faster. So because of that, because we said the XGBoost has a special framework that is, within that framework is integrated features that help in overfitting and multitasking. That helps solve the problem of overfitting and multitasking. That's why The XGBoost is one of those algorithms out there that you find yourself having to most use them in most of the work that you are going to be doing because it has a very good, it's been proven to perform extremely well in most situations. And so therefore, why is it so is because of these additional features that it's within its framework. So now today we're just going to be imagining like, okay, I am saying that it has multitasking, yeah, but then how does it handle the problem of what? Overfitting. How does it handle the problem of overfitting? Because I said the XGBoost framework has an inbuilt system to handle overfitting. So how does it handle overfitting? So let me clear all the drawings. Let's see how the XGBoost system handles overfitting. Now, remember, we said that in the boosting algorithm, we are using decision trees, right? We're using decision trees. And therefore means that if we are using decision trees, that means the algorithms that are going to be trained, and we are going, because we are still under the ensemble technique where we use multiple input from different models to be able to come out with our prediction, where we are talking about the wisdom of the majority. Therefore means that in the case of XGBoost, our algorithms that we are going to be using are decision trees that are going to come together, many decision trees to form what our final model, which is going to be the predictive model. So how does it do that? We said it has an implicit system to handle overfitting using pruning. Pruning is like, I don't know if pruning is double P or 1P. I don't know, I don't know, spell something there wrong. Pruning. Oh, it's 1P. So, pruning to handle that. So the question is, how does it work? Therefore, now, if we are talking about decision trees and we are talking about overfitting, we said that in decision trees, because a decision tree will have to do many splits, and go down and do many splits. And as it keeps splitting and going down, that's how the algorithm becomes, it leads to overfitting. So that means the XGBoost framework has implicitly inbuilt systems to handle the number of splits that a decision tree is going to make. So when is it going to stop splitting and when is it going to continue splitting? That is how it does that. So it has inbuilt parameters that help it to know when to stop splitting and when to continue splitting. Okay, so what are these inbuilt parameters that help it to know when to stop splitting and when to continue splitting? That's what we're going to look at. Wait a minute, let me catch my breath there. I'm just coming from another class. So it uses a system. It uses an if-else system. And it says that if gamma, I don't know how they write it. Wait, we should not laugh here. It says if gamma is less than gain, then split. Then they should split. Else then don't split. This is the condition. How does it know when to continue splitting to handle the overfitting or when to stop splitting? Is if gamma is less than gain, then split. Else don't split. Now the question is, what is gamma and what is gain? What do you mean by if gamma is less than gain, then split? And else don't split. Now, I'll start by saying that gamma, the first thing gamma, this one is a hyperparameter. So it's a value that you choose on your own. Hyperparameter. So gamma is a value that you are going to be the one to set it. And then what is gain? Right? So what is gain? What do I mean by gain? So gain is defined, gain is equals to SS after split minus SS before split. Now you are going to be asking me, what do I mean by SS after split and SS before split? So SS stands for what we call similarity score. Similarity score. So gain is similarity score before splitting, similarity score after splitting minus similarity score before splitting. Again, you're asking me what is similarity score and how do you know the similarity score before splitting and similarity score after splitting, right? Okay, let's look at the similarity score before splitting. If I'm taking my time, know that I'm tired. I've been teaching almost all day. So now, similarity score is defined as, let me use similarity score as SS, okay? SS is equals to sum of residual all squared divided by what? Divided by number of residual. So sum of residual divided by number of residual. So we are saying that gain is similarity score after split minus similarity score before split. And similarity score is the sum of residual squared divided by the number of residual, right? So how do we calculate all of that? Oh, I'm using this funny screen today and it's difficult for me to factor things inside. I deleted that if I remember that our decision tree well, it was something like this. Here we had minus 21. We have something here like this. And then here we have minus 11, minus 26, and what was the other one? Minus what? Minus
21.
I have 21 this way. There was another figure this way. Anyways, it's fine. Let's just leave it let's just assume that there are two values this way. It's fine. So now, the question is, what we are saying is, listen carefully. Once a split like this has been made, the first split like this has been made, right? So we are using H less than 20, less than 30, sorry. Once a first split like this has been made, the question is, should there be another split? Should the algorithm continue to split again? Should the algorithm make so on this branch, so you see there are two branches here, right? We have two branches here. Let me pull up my red column. So on this branch, so the algorithm is going to ask, should I make a split again on this branch? Should I make a split again on this branch? So for it to know whether it should go ahead and split the branch again, it's going to say that if the alpha is less than gain, then it should split. But if alpha is not less than gain, then it should not split. And to calculate gain is similarity score before split, the similarity score after split, minus similarity score before split. And now similarity score is considered as the sum of residual. So let's take the first branch. You remember this was the residual because when we take the when we drew our this thing, this minus 21, because we had, remember we had h like this, h here. And then our residual was the final value that we were going to use as a target for model 2, right? Model 2 was now using the residual at its own target, using h as a feature and then the residual. So it's going to calculate the residual. And what it does is that, okay, let's take this branch for example. What is the sum of residual for this branch? Is minus 21. That's the sum of residual, or if you calculate it as a magnitude. So let's use it as a magnitude, okay? There's no need. So the sum of residual is 21 over sum of residual squared. So you can do 21 squared, I don't know, over. So the idea is that if it is minus, then it's squared. So you take 21 squared. So if you have minus 21 squared, it's going to take away the square. So over number of residual, what's the number of residual? We have, in this case, we have just one residual multiplied by, sorry, I forgot one value. Sum of residual. Then there's another formula here, plus alpha plus gamma. Is it one called gamma? This is gamma. So what is gamma again? Gamma is another hyperparameter. So similarity score is sum of residual squared divided by number of residual plus gamma. You can, and I told you gamma is another hyperparameter. It can be 0. It's up to you to choose your value of gamma. And so if I use my value of gamma as 0, that means my number of residual, how many residuals do I have on this branch? Is 1. So number of residual is 1. 1 plus 0 is 1. So it will be remembered as 1. Madam Pair, what is 21 squared?
$441. 441.
441. So that is going to be the, now, what is going to be the similarity score before split? This is the similarity score after split, right? This is the similarity score after split. It's 441 because we have used only this one. Before split is at this level. And at this level, we had all these values there, this 21, 11, and minus 21. So before split, we are going to have sum of residual. What is the sum of residual? Sum of residual will be minus 21 plus minus 11 plus minus 26, all this squared, divided by the number of residual is 1, 2, 3. Is going to be 3 plus our value of gamma was 0. So minus 21 plus minus 11 gives me minus 32. Minus 32 plus.
Some of it is minus 50.
Pardon.
Minus 58.
So it's going to be minus 50, minus 58 squared. Minus 58 squared.
3,364.
Divided by 3.
1,000.
What's the value?
1,121.
1,121, right? Okay.
Yeah.
That is it for this branch. That's it for this branch. So should there be a split on this branch again? That is the question. Should I split this branch again? So let's see. Well, so for us to split this branch, we are going to check whether the gain is less than the value of alpha. Let's set our alpha as 100, for example. Let's say our value of alpha is 100, right? Our value of alpha is 100. So if you take the gain after split minus the gain, the similarity score after split minus the similarity score before split. That means we are going to be taking 441 minus 1121. So if you subtract this, you will have a value, and that value will be less than 100. And if that value is less than 100, that means there will be a split here. But in this case, it doesn't make sense in this case because we have just one value here. It's just, we are just illustrating, right? I don't know if you're understanding what I'm saying. You cannot split here again because there were two, because if there's one value, you cannot split again. But I'm just saying, I'm showing you how it calculates the similarity score before and after. If you take the similarity score for this branch, for example, let's see the similarity score for this branch that has two, at least a split here will be feasible. So we are going to take the similarity score after split will be minus 11 plus minus 26 divided by 2, because there are two residuals, plus 0 because our value of gamma is 0. So if you do this, what is going to be the answer, Madam Spell? All this square, please. 1126 gives you 37. 37 squared. What's 37 squared?
1,369.
Divided by 2.
684.
684. If you take 684 minus this value, because this was the residual before split, that means, yes, you are supposed to split this one again. So as long as, oh, sorry. Oh, what am I saying? If you take this one minus this one, is going to be greater than 100. So as long as this value is greater than 100, you are not supposed to split this thing again. Let me confirm that formula, that condition again, to be sure that that's the condition. So if gain is less than, yeah, so if alpha is less than, no, the thing is, if alpha is less than gain, okay, yeah, that's what I'm saying, right? So if alpha is less than gain, then split. But if alpha is not less than gain, then don't split. Then split. So in this first situation, okay, this is where I had a confusion. In this first situation, so what was our value here in this first one? I did not even look at it well because I was just working in my head. Our value of alpha is what? 100, right? Our first value, our alpha, I told you alpha is a hyperparameter. So don't ask me why I've chosen 100. I just said it's a hyperparameter. Like all hyperparameters that we've been talking about, is a random value that you choose. And that's why you have to tune it to make sure you get the best value. So if we take 100, for example, as our alpha, and then we calculated the sum of the gain here. Sum of residual here, the gain here gave us 441 minus this. If you take 441 minus this, Madam Pierre, can you please give me this answer? 441 minus 1121 should give me minus 68. Minus 680. Is minus 680 greater than 100?
No.
That means you will not split this one again, because we said if the gamma is less than the gain. But minus 100 is not less than minus 620. So there will be no split here again. There will be no split here. Because the sum of residual, the gain here gave us 441. And then now, gave us minus 680, sorry. So minus 680 is not greater than 100. So there will be no split here. Now let's calculate this other side. When we calculated this other side, we had 680, right? We had 680. Is that correct?
684.
684. And so we took 684 minus, this is the sum of residual after split, I guess.
Yes.
This is the similarity score after split, right? Minus this is going to give us what? A negative number again.
Minus 437.
And that negative 437.
437.
Minus 437, right? minus 437 is not greater than 100. So there will be no split here as well. So this decision tree would have ended here. So there will be no further split on this tree. This tree has ended. But if this condition was actually met, was actually true, then there would have been a further split. And the splitting will stop when this condition is not met. So explicitly, that is how the XGBoost framework calculates to know whether there should be a split or not. It starts by having the condition inbuilt that if alpha is less than gain, then there should be a split. But if alpha is not less than gain, then there should be no split. And what is gain? Gain is sum of the similarity score after split minus similarity score before split. And what is similarity score? Similarity score is the sum of residual all squared divided by number of residual plus half plus gamma. And gamma again is a hyperparameter. You can choose your value of gamma to be anything. This is why when I'm explaining to you a machine learning engineer, you need to understand this working around, because when we go now and now we are using XGBoost, and I'm telling you that I'm choosing my value of gamma to be 0 and my value of alpha to be 100. If I did not explain to you what alpha and gamma is, you will not even know what I'm talking about. So you need to understand what is happening in the background. And the reason why we are taking these values is to help the algorithm prune our trees so that they should not be overgrown, leading to overfitting. Is there any question? Is there any question?
Hello, Prof. I don't know if
Yes.
it's a question. I just want to clarify. So, for the split, I'm not understanding the 100 part. The 100 that we're getting is from the subtraction. Is from the subtraction to get the gain, right? From the similarity score after
Madam
split
Pearl, I said
minus
100 is a hyperparameter. I said this is a hyperparameter. This is the value of alpha. This one. It's a hyperparameter. It's a value that you choose on your own. I can choose to have 10. I can choose my alpha to be 10. I don't know if you understand what I'm saying.
I'm understanding that part. My issue now is when we came to calculations, because it's after split and it's before split. But we're
After
doing
split.
for the left
After
and the
split.
right side.
Yes,
So
you are doing for the left and the right side.
I not get it. So that's what it means. The left and right of the tree. Because I not get the before and after split.
If I get my tree like this is my tree. I split my tree. Remember, let me build a situation. Assuming I just get if I just get my data like this. If I just get my data like this, on this data I have let me say H, say 10, 15, and 16. And then let's say here I have maybe salary, right? And I have something like 20, 30, and say 36, for example, right? And so if I calculate what is this, what the first algorithm will do, the first M1, this is what M1 will do, this is what M1 will do. So M1 will calculate the average of this 20, 30, 36. What is that? 20, 30, 36. 20, 30 gives me 50 plus 86. What's 86 divided by 3?
28.6.
So let's just put 28, for example, so that we avoid the 0.6, so that we don't confuse ourselves. So let's say this is going to be pret 1. Pret 1. Now, after pret 1, I have to calculate residue 1. I have to calculate residue 1. And the residue 1 is going to be actual minus predicted. So R1. So in my residue 1, I'm going to have the actual minus the predicted value. So I'm going to have 20 minus 28. This is going to give me minus 8. 30 minus 28. This is going to give me this is going to give me 2. And then 30 minus 36 minus 28. This is going to give me 8. Is it 8? 36, 2, 10. Can somebody punch this for me?
8.
What's the value? Is 8?
8.
Okay. So you see, this is going to be my R1. And so this is what M1 will do. So M1 will now take this H and this R1. That means we are now going to have H and R1, residual 1, being sent to M2. So this is now M2. Sent to M2. So you have 10, negative 8. You have 15, 2. And then you have 8. 8 here is what? Is this 16? Sorry, this is 16, not 8. You have 16. 16 here is what? 8. So now when it goes to M2, M2 now, this is the target. This is going to be the target for M2, and then this will remain as the feature normally. So what M2 is going to use is that M2 is now going to classify this target based on the feature, which is H. So we just want to draw our funny decision tree because it's not going to just calculate the average again. So it's actually going to now take a decision tree and explicitly split the data. So we were just M1 just, that's why this is called the base model. The base model only calculates the average. And I was telling you people that in these boosting techniques, the algorithm that is used is a decision tree. It's a decision tree. And so the decision tree is going to now start from M2. So when you give this data to M2, M2 is going to now classify the target based on the feature. And this feature in this case is H. So assuming that it now creates a classification boundary for your data and says, and in your classification boundary is going to say that, let's say it says H now, H less than 15. Say H less than 15. This is your classification boundary. That means everything less than 15 is going to come this way. And so how many H's are less than 15? It's only one H that is less than 15. And what's the target value for that H? It's negative 8, right? Right? It's negative 8. So here I'm going to have negative 8. And now, what are the H's that are greater than 15? I have 15 greater than or equals to 15, for example. What are the H's that are greater than 15? Let's say greater than or equal to 15. So the target values for those will now be what? 2 and 8. 2 and 8. This is the decision tree that R2, M2 will do. Now the question is, in this case, the question is, within the XGBoost framework, there's going to be a question to know whether this decision tree should continue being split or not. For example, you have to, normal, this is not a pure node because we have 2 and 8 here, because normally we are supposed to have one value, pure node. Because somebody should end up in a pure place, like it should not be a blend, whether you are in 2 categories, because this is a categorical case. So you are ending up in a pure category, but these are 2 categories here. So anybody who is greater of age, greater than 15, greater than or equal to 15, you are now going to be doubting whether is this person going to end up in category 2 or in category 8. But it's sure that anybody who is less than age of 15 ends up in category negative 8. That's sure. But this way, now, so the tendency is that for it, by default, a decision tree will go on again to now split this data again. It will do another split here. Now, based on, normally the features are normally more than one. You have age, you have sex, you have a lot of things that will be taken into consideration before the target. So now, based on information gain, is going to decide which feature is going to start with as the root node. We talked about all of that. So once you use the first feature, which is going to be used for the information gain to do the first split, after the feature with the highest information gain is used for the first split, is now going to go further again and calculate the information gain for the next split. And whatever feature it is that it will be using as the next information gain for the next split, before it does that split, is going to first of all check whether that split is supposed to be done or not. Is this split supposed to be done or not? And how does it know whether it should do a split or not? It says if gamma is less than gain, then split. Else, if this is not true, then don't split. Now, what is gain? Gain is SS before split, sum of SS before split, before split, minus SS after, no, sorry, I'm mixing it up. Gain is going to be, and what is gain? Gain is equals to similarity score after split, minus the similarity score before split. And what is similarity score? Similarity score is equals to the sum of residual, in this case R1, all that squared, divided by the number, let me use hash as number of residual, then plus the value of alpha of gamma. And gamma again is another hyperparameter. This alpha here is a hyperparameter. You choose the value yourself. And the gamma down here is another hyperparameter. You choose it yourself. In our case, we chose this value to be 100. And we'll choose this one to be 0. And so how now a split has been done. This is the first split that has been done based on information gain. The first feature with the highest information gain has been used to do the first split. So the algorithm, the framework is going to check, is there going to be another split? Remember, splits are per branch. There's going to be a split here. There's going to be a split here. So the question is, it takes the first branch. Should I split this branch again? This branch is, am I supposed to split this branch again? For it to answer that question, it has to calculate and know whether the gain on this branch is less than the alpha or not. If it is not, it will not split. If it is, it will split. Is it clear? And how do you calculate the sum of residual on this branch? Sum of residual is the residual. 8 is the residual. This is the residual now. This is the residual. What's the sum of the residual? So here I will have 8 squared, minus 8 squared, sorry, divided by the number of residual. How many residuals are on this branch? It's only 1. And my alpha is 1. So I'm going to have 1 plus 0. Sorry, 0. So 1 plus 0. So this is going to be 64. Is it 81 or 64? It's 64. 8 squared is 64, right?
64.
Ah. Okay. So this is going to be 64. So this is going to be 64. And so it's going to check. This is the sum, this is the sum of residual after split. This one gives you after split. Before split, what was the residual? Before I made this split, what was the residual at this level before I split? Because I'm calculating the residual now at this level. What was the residual at this level? The residual at this level was -8 plus 2 plus 8, all that squared, divided by number of residual. The number of residual here is 3 plus 0. So I'm going to have 3 plus 0. So -8 plus 2 gives me 6. -6 plus 8 gives me +2 squared gives me 4. 4 divided by 3 gives me 1.666. So that is going to be my residual before my similarity score before split. So my similarity score before split is 1.66, and my similarity score after split is 64. So 64 minus 1.66 should give me something like 64 minus 1.66 should give me something like 62.4, something like that. 62.4. Now, to know whether there should be a split on this branch again is now going to check, is this 62.4 less than my value of alpha that I stipulated? The answer is no. 62.4 is not less than 100. It's not greater than 100. It's not greater than, because if alpha is less than gain, but gain is 62.4. 100 is not less than 62.4. So there will be no split here. Now let's calculate the similarity score on this other branch. To calculate the similarity score on this other branch, similarity score after split here will be 2 plus 8. That gives me 10. 10 squared is 100. So I'm going to have 100 divided by 2, because there are two, number of residual is 2. 2 plus 0, my value of gamma is 0. So I'm going to have 50. So my similarity score after split on this branch is 50. And my similarity score before split remains the same, is 1.66, right? So I'm going to now take 50 minus 1.66. What is going to be the value? The value is going to now be 47.4. Is 47.4 greater than 100? No. So there will be no split. There will also be no split here. So this tree has ended here. So that is how it uses it to stop, to prune the tree. Is it clear? No, no, you are just quiet like this. I've seen my own today.
No,
It's okay, Prof.
Do you now understand how the XGBoost framework helps to solve the problem of overfitting by pruning the tree? What does it mean to prune? If they say a tree is overgrown, you prune it, you cut some of the branches, right? It prunes the tree by cutting out some branches. And it cuts the branches by trying to limit the number of splits by calculating the gain and comparing it to a stipulated value of alpha. Madam Pe, you clear or you not clear?
It's clearer. It's better now.
It's better now.
Yes.
That doesn't sound promising. Ask your question.
Yeah. So on the, it's just I cannot point it. There's this part where we have -8 in bracket -2 plus 8 squared divided by 3 plus 0.
That's
Yeah.
that's the similarity score before split.
Okay. It's before split for the -8 part. So the -8 is out of the
Again, when
bracket.
you are asking me for the -8 part, see, we had this tree like this, and we
Prof,
split through this
Prof,
tree
Prof,
once. Wait, let me
Prof.
explain this one. You had the first split here. There are two split. They split here. Before you do this split, there was a residual here. Here, there was a residual here before the split. And then this split happened. So now ask your question.
Yeah, that in the formula, right? Like what you
Mhm.
wrote, is it like
Mhm.
bracket -8, open bracket -2 plus 8 bracket all
You should
square?
have known that. You should have known that I'm using my mouse to write now, Madam Pair. And sorry me.
I'm not. I'm like, okay, then my problem is why is it -8? Ah, okay. So we have -8 to.
What was the residual before split? Is this not the -8?
Yes, I'm understanding it now. My issue was that extra bracket. It was confusing me, but it's okay now.
I'm telling you that I'm using my mouse to write. You two, you are not beating me.
Actually,
Yeah,
prof.
I'm not beating me. There's a plus here. Is it making sense to you now?
Yes.
Because before you split the data, this was all the data now before you start splitting. So this is the residual in that data before you started splitting. This is the data. I think this is what we send to R to this is what we send to this is the data that we send to M2 now. And this were all the residuals there before splitting. But after splitting, there was a residual that went to one branch, two residuals went to the other branch, right? So do you want to split that branch again? Take note, the splitting is per branch because you can split one branch and not split another one again. So it has to calculate the residual as per the branches. You understand?
Yes, I understand now, prof.
Hello,
Any
Prof.
other questions again? Yes. Who is that? Is that Benito or Dr. Kifa? Who is that?
It's Kifa, Prof.
Okay, Dr. Kifa.
Yeah, good evening. During the future from the first model, that's M1, the age, it's a little different from what we sent to M2. We had 10, 15, and 8, and then in M2,
Oh, sorry, this is, you are still suffering from the same problem that I'm using my mouse to write. This is 16, sir.
Okay.
I'm still
All
using
right.
it. Don't bother. I'm using my mouse to write. I did not use my stylus today. My bad.
I have a question.
Yes, Dr. Tony, I've been waiting. You wanted to staff me and then come and ask at the end.
No, my one is basic. So, Prof, is
Yes.
there, when you talked about, is it gamma or something that you have to, that you can just choose a random number, like any number of your choice, where you said you can choose 100 or 10. So is there an understanding behind the number that you choose? Like, is that something that you've known or that you know that will not make you say, okay, you know what? Okay, I've looked at this thing. I think I should choose 100 or 50. Or you just say, no, let me just choose 50, does not matter. That is one question. Then another thing, when you say hyperparameter, what is it called hyperparameter? And that is it machine learning terminology for choosing any value of your choice? That's my second question, sir.
I think it's a machine learning terminology as per hyperparameter. What does it mean? Why do they use the word hyper in the first place? Well, okay, but the idea behind hyperparameters is that these are values that their decision is based on the person working. Okay. The choice of what value to use is up to you. And that is why, since there is no defined value for that parameter, since there is no value for it that is set as this is the best value or this is the suited value to always use, it is advised that you tune it. Tuning means you have to change different values. Change 100, try 50, try 10, and see which of the values that you are changing will give you the best performance. You understand?
So you have to tune.
Yeah,
test
that's the meaning
different
of
stuff.
tuning. You tried 100, try 50, try 30, try 10, try 1, and see, try 0.5 and see which of them is going to make sense, which of them is going to make the performance better. Because, for example, look at this one. The value of alpha here determines how much your tree will be splitted. That's true, right?
Yes, yes.
The value of alpha determines how much your tree will be splitted. And you know that how much your tree is splitted directly affects the performance of your model. That's true, right?
Yes.
And so the question is, now, which value of alpha is best? Do you know?
No, that was why I asked the question.
Good. So there is no fixed value to say is best. So you are going to try different numbers and see which of the numbers gives you the best performance. And we notice in some situations, like, there are always default values. I don't know what the default value for alpha is. Maybe when we go to the practical session, we'll check and see what the default value is. There are always default values. And most of the time, these default values are values that experts have tested, and these values always perform well. They just set them as default. And in case where there's no default value, they put none.
So, and this value now that you choose is now called hyperparameter.
Yes, because that value is not based on anything. You are the one now who is going to be changing that value. We've seen plenty of situations of hyperparameter. For example, when we're doing random forest, we see n estimators, number of decision trees you want to use. By default, they are 100. But do you think that that's the best number? When we're looking at gradient descent, you remember gradient descent? When we're looking at gradient descent, we choose the number of epochs, right? And our learning rate. Is learning rate, the learning rate and the number of epochs, these were hyperparameters. We had to tune them because we did not have a specific value for them, right? Is that clear?
Yes, it is. Thank you.
Yes. Any other questions again? Any other questions again? Is Benito on the call? Madam Prudence. This is not where you just quiet, so now I know. Is the ministry moving to a permanent location?
Yes, Prof.
Is Madam Prudence, the ministry is moving.
I'm trying that you should move.
Your friend that it should move. Please let it be moving, okay?
Yes, Prof.
Awesome. Now, the last thing here is that once it does this, the way it now calculates its final prediction is not like we know. For the gradient descent, for the XGBoost, it calculates it using a different formula, and that's the last thing I'm going to be teaching today. So it uses the formula final prediction is equals to sum of residual divided by number of residual. Number of residual plus gamma. There's no square here. So Don't mistake it. Is that okay? Is that okay?
So no square.
Yes.
There's no square. This time around, there's no square because the first one we had a square. You remember the one where we were calculating similarity score? There was a square here. There's no square here. This one has no square. So now, so once your tree has been splitted and ended where it's supposed to end, for example, assuming your tree ended like this, and then you are going to now have your final prediction. All right. We are now going to have your final prediction, and that is how, let's see how we get a final prediction. No, this is not your final prediction, it's your prediction, sorry. It's not final prediction. This is your prediction because your final prediction still remains as your final prediction still remains as spread 1 plus spread 2 plus learning rate spread 2. It still remains like this, but your prediction now. So this is what we've calculated. So this is your prediction. How do we get your prediction for? So this is now M2, right? So let's come. So this is M2. So let's just transfer this data down here, please. So here we have H. We have H. We have 10, 15, and 16. Dr. Kifa, I hope you are now seeing 15 and 16. Oh, don't see something else. R1 is going to be minus 8, 2, and 8. So now prediction. Spread 2 is going to be sum of residual over number of residual. So for this case, $10, you come to the tree. What is the sum of residual here? Is -8 divided by number of residual is 1 plus gamma. Our gamma was 0. So -8 divided by 1 is -8. So here I'm going to still have -8. Here, if you take 15, it comes to this branch. What's the sum of residual here? 16 divided by number of residual is 2. It's 16. So here I'm going to have 8. That's 16 divided by 2. Here again, if I take 16, it comes this same way again. So I'm going to have 16 divided by 2. So here I'm going to have 8 again. So this is my prediction 2. And so my final prediction now will now be following the same formula. Pred 1 plus learning rate multiplied by Pred 2. So what was my Pred 1? What was this average? 28, right? 28. And so if you take learning rate, let's use 0.1 as our learning rate. 0.1, sorry, this. It's another hyperparameter. You know that already. So 0.1 multiplied by 8. What's 0.1 multiplied by 8? It's like 8 divided by 10. 0.8, right? And people.
0.
0.8.
0.8. 0.8.
0.8 now, that's negative 0.8 plus 28. That should give you what? 27.2, right? And my people, here you are going to have 8 multiplied by 0.1 is going to be 0.8. 0.8 so you're going to have 28 plus 0.8 now should give you what? Should give you 28.8. This one too should give you 28.8, 28.8. So residual 2 now. Your residual 2, R2, will be equal to the actual, which is 20 minus this one will give you minus 7.2. 30 minus 28.8 will give you 1.2. 36 minus 28.8. What's 36 minus 28.8? Ampere. You're not responding.
7.2. 7.2.
Pardon?
7.2.
7.2.
So you see that our residual is reducing now. Our residual 1 was 8. Now it's 7.2. Our residual 2 is 2. 1.2. 8. 7.2. So if you continue, that's how the residual will be reducing up until the last one where your residual will now be insignificant. Is clear or you know clear?
So I'm not really clear with the calculation of PRED 2.
PRED 2. PRED 2 is sum of residual over number of residual plus alpha. Our alpha is 0. Our gamma is plus gamma, sorry. So take 8, for example. This is our tree. We are using this tree. So take the first one. We are using what is that? We are using 10, the h of 10. When your h is 10, which branch do you go to? You come to this branch. What is the residual on this branch? 8. What's the sum of 8? Is negative 8, sorry. What's the sum of negative 8? The sum of negative 8 is negative 8. Divided by the number of residual is only 1. So it's only 1 plus your value of gamma is 0. Negative 8 divided by 1 is still negative 8. That is why it's negative 8, right? And if you come to the next value, h equals to 15. H equals to 15 comes to this branch. When it comes to this branch, the question is, what is the sum of residual here? There are 2 residuals here. What is the sums? Oh no, sorry. This was supposed to be 2 plus 8 is supposed to be 10, not 16. Why you people are not helping me? It's 10 plus 10 divided by 2. So here we're even supposed to be having 5, my people. I was even shocked that the difference was just we're having 5 here, right? And so 5. So when you have 5 now, this gives us 5. So that is our final prediction. So now here we are now supposed to have, instead of having 0.8, we are going to have 0. We are now supposed to have 0.5. 0.5. And so this one, if you add 3 here, 1.5. You add 3 here, 7.5. Right? Yeah, Dr. Kifa.
Yes, sir.
Does it make sense now?
Yes.
Any other question again? Okay, please, let's leave it here for today. We'll do the practicals tomorrow. I'm completely exhausted, okay? Not tomorrow. We'll do the practicals on... Tomorrow is what, Tuesday?
Yes, tomorrow is Tuesday.
We're supposed to have a class tomorrow, right?
Yes.
Okay, well, let's do the practicals tomorrow. And then we move ahead. Is that okay? I'm completely exhausted today. I cannot go into the practicals now. Okay, thank you very much. Let's meet tomorrow, same time. And we continue from there.
Okay, Prof.
Bye-bye.